So can both of you hear me? Like, 주현 씨 잘 들리나요? So Robert, can you hear me? Thanks. Okay, so let's start today. Okay, so let me start with some story about this result that I'm presenting to you. So maybe side remark. So one of the major problems in the theory of programming languages is to come up with, justify why untyped lambda calculus, which you're gonna see soon, is gonna be, it has some solid mathematical foundation. So around the end of 1970s or maybe around 1980s or something. I may be wrong about the exact dates, but in the very early days of programming languages, what happened is that Christopher Strachey in Oxford, they tried to come up with a more mathematical solid foundation of existing programming languages. So what Strachey did was that he used so-called untyped lambda calculus to define the semantics of many programming languages. So one of which I heard became a forefather of the C programming language that you see, and as well as some functional languages. By the way, Strachey came to know about lambda calculus from Roger Penrose, who got a Nobel Prize this year, the physicist who worked on these black holes and so on. He once worked on the programming languages with Christopher Strachey. So, but what happened is that when Strachey kept doing it with his colleagues, so Dana Scott from the US, who was was a logician, he looked at what's really going on by Strachey and his colleagues, and then he said, what is the really mathematical foundation of the meta language that you are using? In particular, at the time, what Strachey is using is, in a sense, assume there is some space D, which is isomorphic to its own function space, and perhaps something more. And this is the kind of space we're gonna use when you study functional languages, maybe from this Wednesday or maybe from the next week. So this was a big open problem, and Strachey and maybe Dana Scott, they tried to they worked on this problem. So what I heard from Dana is that when at one point Scott decided he wanted to spend a semester. He was a professor in the US, but he wanted to spend a semester in Oxford or maybe 1 year in Oxford, and giving us a series of seminars about what's the key difficulties in solving this problem and what are the current approaches at the time. So the story I heard is that he gave a series of graduate level seminars about this open problem in programming languages. And in the middle of this seminar series, which is a bit like a graduate level course, maybe not like this, but more advanced one. But at some point, he realized actually he can solve this problem. So initially, the plan of the of the seminar, but of the course, was to present the issues involved in solving this one big open problems in programming languages. But it turns out in the middle of the course, the theme of the course changed, and it became to present his most recent work on the solution of this space. So what I heard from John Reynolds, who is the author of this textbook, and he said, once Scott solved this open problem, and it became kind of big shot, like a very hot news among the people working on programming languages at the time. So I'm not sure it's exactly the same seminar or the one after that, but people realize this is a kind of one of the really big developments in programming languages. So what John said was when he was visiting in the UK, I mean, lots of people went to Oxford to attend the Dana Scott seminar where Dana presented the solution of this recursive, I mean, his most recent solution for how to solve these recursive domain equations and that this big open problem in programming languages. And later, lots of people polished what kind of the initial idea of Dana Scott. So the version that we are presenting, this categorical, this fixed point theorem, is one of the later developments about what's really going on in this setup. And then we're gonna look at instantiation with the so-called domain of embedding projection pairs. That's not the most recent development. I mean, the most recent one is based on a bit more abstract notions, so-called compact categories, and then some order-enriched categories and so on. That has a much more kind of, in some sense, if you get used to it, it's much easier to use. But I mean, this is what we are going to look at is a bit more polished version of Dana's solution. Okay. So here's a quick reminder about what we did before. I said one objective of, okay, so why did I talk about this slide remark? It's because the whole of this lecture is about how to construct, given F, how to construct D that satisfy this fixed point equations, although it's isomorphism, it's really about fixed point equation over spaces. So here's a reminder about what we covered so far. I said, in one way to solve this type of fixed point equation is to mimic what we learned in the domain theory. Okay. So our general strategy was to generalize what we did for fixed point theorem in domain theory. And in this theorem, although it's a bit of math, it's not very hard to understand. And then we look at there are some ingredients in this fixed point theorem, which are domains. It is partially ordered sets with list elements and chain complete. So every chain has its list upper bound. And there is the other ingredient is a fixed continuous functions. And they are monotone functions such that preserve list upper bounds of chains. So, and then once you have these two parts, then we said there's a list fixed point. There is. And actually, I said that last time we talked about there's a bit more general result, which said there's a list prefix point. So it's a list element among the prefix point. So that's something that we talked about. And then our strategy was to generalize what's really going on here. So the generalization that we looked at, I mean, we said partially ordered set. We can generalize to our categories because categories can be seen as a generalization of partially ordered set. And then the list elements in a category is generalized to initial objects. And then chain gets generalized to omega chain in categories. They were just collection of countable collection of objects and morphisms in the categories of this form. And so on. So we have object x0, x1, x2, and so on, and morphism f0 goes from x0 to x1, f1 that goes from x1 to x2, and so on. And because the morphism is a generalization of something is less than the other, this corresponds to a chain which start from x0, becomes x1, x2, and so on. Okay, so that's just our generalization. And then to talk about completes, which is every chain has a list upper bound. We talked about Cocorn, which correspond to an upper bound of a chain. And we also talk about co-limit or co-limiting Cocorn. This corresponds to the list upper bound. And Cocorn was the sum for this chain delta was some object y together with let me create some space. So it was some y together with morphisms, say G0, that goes from x0 to y, G1, that goes from x1 to y, G2, that goes from x2 to y, and so on, such that every triangle that you see, so you can go from x0 to y directly by using G0, or you first apply f0 and then followed by G1. So this the triangle, the commutative diagram commutes. The second commutative diagram commutes, and so on. So all these diagram commutes, then we say this y is Cocorn. And we said some Cocorn is co-limiting. Well, so in short, we say something is a co-limit if it satisfies the following property. So we said this y is a co-limit if whenever, I think let's write it another one. Suppose I have another Cocorn which is say H0, H1, H2, and so on. So then we said Z, which is another Cocorn, is a co-limit if whenever we have a co-limit like y there, Cocorn like y there exists, let me first activate chat. There exists a morphism that goes from Z to y. There's a unique morphism. Let's call it K. There's a unique morphism that goes from Z to Y, such that every, this HI and GI commute by K. Okay. Or another way to say this, GI can factor through K. So what this means is that if we look at from particular X, like X2, if you look at one way to go to Y by G2, another way, which is by H2 and then K. And these two roots should lead to the same morphism. Okay. So that was the definition of co-limit. So Z, Cocorn, satisfying this extra property is called co-limiting, and we say this is co-limit. And that's a generalization of list upper bound of a chain. And then other things that we talked about is that to generalize these continuous functions, monotone functions get generalized to functors. And then preserving the list upper bound of chains correspond to preservation of co-limits of omega chains. And if functor satisfies this extra property, we call it omega continuous functors. So what this preservation means is that if we have a, so this preservation means if we have chains, and then we have a co-limits of the chain, say 0, H1, H2, that's in category C. Now, if I have a functor that maps everything in category C to something in category D, then I said the functor maps this chain and this co-limit to chain and cocorn. It doesn't have to be co-limit, but it's a cocorn. So we have f of x0 and the functor f of x1, f of x2, and here f of small f0. So, and fz becomes like this. H1. This is f of h2. So this z is a co-limit. Then if f is a functor, it's guaranteed that this f of z is a cocorn. But it doesn't have to be co-limit. So continuity, omega continuity, means that this cocorn also should be co-limit. So that's what this omega continuity is telling us. Okay, so that's what we learned before. So then once we have using this generalization, we can actually formulate this least fixed point theorem. So that's what we're going to do. So here's a statement of least fixed point theorem. Categorical list fixed point theorem. And the theorem say something like this. Suppose we have a category C, which is chain, which have a initial, it's a category with initial objects and chain complete, which means that every chain have co-limits. Okay. And then we have a functor f that goes from C to C. This is an omega continuous functor. So these are the assumptions. So the first assumption corresponds to we have a domain. Second assumption corresponds to we have a continuous function. And then under this assumption, the conclusion of this theorem say there exists an object x fixed in the category C such that it satisfies two properties. So it's a fixed point, and so I think it's better to say it this way. There is an object. Also, there is a morphism. I wrote eta that goes from f of x fixed to X fix in the same category C, such that really intuitively we want to say X fix is a fixed point, and then second is a least fixed point. So the first statement corresponds to X fix is really fixed point. So the first statement said that eta is essentially isomorphism. So there exists, say, rho that goes opposite direction of fix. I mean, this is a morphism in C, such that it's the inverse of eta, which means if I compose with eta and rho, that's gonna be identity morphism in f of x fix. And if I compose the opposite direction, so eta and rho, that's going to be an identity morphism in x fix. So that means this eta is an isomorphism. I mean, that's really similar to say x fix is a fixed point. I mean, if you look at the one above, here the statements that we are looking at is that this domain D is isomorphic to f of D. And that's the first statement really corresponds to that part, to that part that I mentioned. The second part is about it's a least fixed point. Okay, and this is part maybe it's not a bit strange to some of you, but I mean, once you get used to it, I mean, this looks you may feel that this is a natural way to formulate it's a least fixed point. And it said for every eta prime, that's a morphism from some y, f of y to y. That's a morphism in C. Okay. What does this mean? This means that y is intuitively, it's a generalization of saying y is less than or equal to f of y. So if that's the case, so then there exists a unique h that goes from x to y, so a morphism in C, and it satisfies the following diagram commute. The diagram say if we have f of x fixed, here's x fixed, and we have x fixed, y, f of y, so it's eta prime and eta, and for x fixed we have this h is claimed to be a morphism from x fixed to y, and if we apply f to h, then we will have a morphism that goes from x fixed to f of y, and this diagram should commute. So what does this mean intuitively? Intuitively, say there are two ways of arguing why f of x fixed is smaller than or equal to y. Okay? So why this guy is smaller than or equal to y over there. And one way is by composing the h and eta. So that's a one way that goes to correspond to moving this direction. Another way correspond to moving the other direction. So we compose with eta prime with f of h. And then this statement said there's no ambiguity between these two ways of viewing. The y is, this object y is smaller than or equal to f of x fixed. Both leads to the exactly same morphism, so they are compatible with each other. And then more practically, this is, I may mention this or not, but this is some, this corresponds to something that we studied before, which is called initiality. Of the initial algebra that we talked about. And then when we define this double lifting operator and then this dagger operator when we play with this domain omega, that the operator is using this particular property there. So although it looks abstract, it's actually quite very useful to whenever you want to do something with this fix, this x fix which exists, but if you want to do something about it, then often we end up using this second property. Okay, the question becomes how we can prove this theorem. So just let me state the theorem again. The theorem says if you have a category C that has the initial objects and chain completes, and then also we have a functor f that's omega continuous, the functor is on C, then there is a least fixed point of the functor. So the first statement said really this x fix is a fixed point. So that's what this first statement is telling us. Second statement is telling us actually x fix is the least fixed point, or the more generally x fix is the least prefix point. Okay, that's what the second statement is telling us. Okay, so then the question becomes how we can prove this theorem. So the proof of this theorem that will form the major part of today's lecture is very similar to the proof of the least fixed point theorem in the domain theory. So, and then I'm gonna maybe remind you of the proof of least fixed point theorem in the domain theory, and I will show you how it's generalized in this context. But before doing so, let's think about what we need to do. Okay, in this theorem, there are a few things that this proof of this theorem is very constructive, which means that there are a few participants in this theorem, which we're gonna construct explicitly. So the one participant is this x fix. It's in a sense the main participant of this theorem. Another participant of this theorem is eta. So we're going to construct x fix and eta. But we're also going to construct this row explicitly in the And then also the fourth thing that we have to do is assuming when we are given eta prime, which satisfy which is a morphism from f of y to y, we have to construct this H. So the proof of this theorem boils down to constructing these four elements and then, four participants in the theorem, and then show that these participants have the certain properties. So before going to the proof, it's somehow out of sync. Let's wait a little bit. I think the system is not quite in sync. Very strange. Okay, so let's just do this. It's a bit strange. They are not quite the software. There's a delay. Okay, let's get rid of this. The same problem. Okay, just ignore these boxes. And then let me give you the proof about, give you a reminder of the proof. So here's a reminder of So give me a second. I think something is not quite right. Okay, so so here's a reminder of the proof. list fixed point theorem in domain theory. So in that context, we have a D, which is a domain, and we have a continuous functions that goes from D to D function, and we have to construct this fixed point X there. So how did we do it? So the way, so then the first question was how to construct the list fixed point of F. So the way we did it was we constructed a chain. The chain starts with the smallest element bottom there. And then we apply F to bottom. And that is small, I mean, this bottom is smaller than equal to F of bottom. That's because bottom is the smallest element. Now F is monotone, so if you apply F to both sides, F of bottom is less than equal to square of bottom. So instead of writing like this, we said, okay, this is the same as square of bottom. And then essentially we repeated the process with this F of bottom and F square of bottom. So if you apply F again, so that's going to give us this, the next element in the chain. So if you keep doing this, then this will generate a chain. And that chain, because D is a domain, it will have a list upper bound. And we said that list upper bound is going to be X fixed, the fixed point of F. Okay. And then later, if we have some Y, which is another prefix point, suppose we are given Y, such that F of Y smaller than equal to Y. The way we show Y is smaller than, so now X fixed, this is, we should, well, what we want to show. Then the way we did it was we just looked at, we showed that Y is an upper bound of this chain. So we noticed bottom is less than equal to Y. Then if you apply F, F of bottom, because F is monotone, Y. And then because of this relationship, you can just replace it to Y. And we do it the same one more time. Then we get F square of bottom is less than equal to F of Y by the monotonicity of F. But then using this property again, then we get Y here. So this gives us Y is an upper bound. Of the chain. So because X fixed is the least upper bound, as we see here, any upper bound Y should be Y X fixed should be less than equal to Y. So that was how, roughly speaking, our proof worked. So we are gonna generalize this in our categorical setting. Okay. So there's the proof. Fixed point theorem. Well, actually, I think the better way to really do the proof is to prove the categorical fixed point theorem by generalizing this. So we have category C in the categorical fixed point theorem. We have a category C as well as a functor F. So the theorem, the user proof of the user fixed point theorem told us how to build the fixed point, and then Okay, so it also told us how to build something like eta here. I mean, no, something like h here. So by using, so here's an exercise I want you to do. So using the analogy by just generalizing the proof of the usual fixed point theorem, try to construct, I mean, this x of fix. So I'll give you, so try to construct this guy. So that's I'll give you maybe 3 minutes to do so. So the way we constructed in the domain theory was we start with the bottom and we constructed a chain and we used the least upper bound of the chain to define this fixed point of f. So try to construct this x fix, which is an object in a category, by mimicking what's really going on in the proof of this fixed point theorem in the domain theory. And if you can solve this, think about how you can build something like h here. Because, I mean, they are, both of them have directly, construction of both directly correspond to what's really happening in this fixed point theorem, in domain theory. Okay, so let me show you how to do this. So we want to construct this x fix and h. So here's how you can do this. So how to construct x fix? Which is an object in the category C. So our proof construction is actually very, very similar to what's really going on in number 1. So we start with the initial objects in the category XC, which is initial objects. In the category C. And then we think about objects that's obtained by applying f to x0. And the definition of initial object is that's an object from which to any of the object there is a unique morphism from x0. So that's the definition of initial object. So because x0 is an initial object, there exists a unique morphism that goes from x0 to f of x0. I mean, this f0 exists because of the definition of initial object. That's very much like in domain theory, bottom is the smallest element, so that's why bottom is smaller than equal to f of bottom. Now, if we apply functor f to f0, the x0, f0, and f of x0, so everywhere in this diagram. So then if we apply functor f, then we get f of x0, capital F, and let's use a G, because I keep. So capital F applied to G0, and F applied to f of x0. So we have something like this. Okay. And then if we apply functor f again, then we're gonna get f of square of x0, square of g0, f cube of x0, and so on. So we can have something like this. And if you put all of these together, we can actually generate a chain. So if you put in what we get in the first step and what we get in the second step, then we have square of x0, f of g0. The third step, then you get f of cube of x0, square of g0, so on. So we can keep going on. And that's very, very similar to actually how we constructed a chain in the proof of domain theory. So fixed point theorem in domain theory. But here things are all, I mean, in the categorical setting, much more general setting. Okay. So we created a chain. So this is omega chain, delta in a category C. Now, because category C is has its chain complete, there should exist x fix, which is the core limit of this chain, where we have a morphism from every element, every object in the chain to x fix, such that the morphism in the chain and the morphism from chain to x fix, they commute with each other, they're compatible with each other. So we have h0 here, h1 here, h2 here, h3 here, and so on. And they're compatible with each other. And this x fix is going to be the fixed point that we are looking for. Okay, we're going to prove that this x fix is a fixed point. Okay, now that's, before doing so, let's do the step 2, part of step 2, which is related to this guy. So the step 2 tells us the generalized version is that we are given, in this case, a morphism, okay, say, let's call it K and now eta prime, from f of y to y. This is a morphism in object C, the category C. Okay, so we are given a morphism eta prime, and then what we want to do, so we want to construct appropriate morphism that goes from, say, let's call it H, that goes from x fix to y. So that's what we want to do. Let's call it K instead of H. So how you do it? And if you look at the proof in this fixed point theorem in domain theory, the proof scheme was we first show y is an upper bound of the chain that we used in step 1, And then by referring to x fixed is a least fixed point, we show that what we want. And we do exactly the same thing here. So we first show that by using this eta prime, we're gonna construct a cocorn of the chain that's going on here. And then we will use the fact that x fixed is the co-limits. So that's why we have a morphism like a K that we want to build there. Okay. So then the question becomes how we can build a cocorn just using eta prime. And that step is very, very similar to what you see in step 2 on the top. So we first start with x0. And because x0 is an initial object, there is a morphism that goes from x0 to y. Let's call it G. It's not very good, but let's call it just A0. So that's a morphism that goes from x0 to y. Yes, because x0 is the initial object, we have something like this. Now, if we apply the functor f to everywhere, then we have f of x0 and f of y. And then because x0 is the initial object, that the morphism from x0 to f of x0, that's exactly the g0 that we are using on the top. And from f of x0 to y, we have a f of a0. Okay, so we have this much, but now we are using eta prime to complete this diagram. Now this diagram commute, that's because A0, the commute means that we have two ways of going from A0 to Y. One is directly going bottom, like here. And the other is to go via G0 and f of A, A0, and then this eta prime. That's just not the other way to go there. But they have to be the same. That's because x0 is the initial objects. From initial objects to any other object, there exists only one morphism. So both A0, the other guy written as a purple, they both have to define exactly the same morphism. Okay. Now, if you apply functor to this diagram, then we're gonna obtain functor preserve commutative diagram to commutative diagram. So we have f of x, this one, G0, square of x0, square of y, f of y, f of eta prime. So essentially, I apply f to everywhere in the diagram on the left-hand side. A0, square of A0. And this diagram comes in because f is a functor. So if you put these two things together, and then we can keep repeating this, and that means, so now one thing you notice, the say this part and then this part are exactly the same. So we can overlap with each other. And if you apply functor to the diagram here, you get another diagram where there's another, the part that's going on here and the part you're obtaining on the other side will be exactly the same. So if I put all of these things together, then this is the diagram that I'm gonna obtain, which is 0, y, a0, prime, g0, and then here's g0, 0. F of eta prime. And the same thing again. Then we have this. Square of eta prime. Square of G0. And all this diagram commutes, this diagram commute, this diagram commute. And then now, if we have a very complicated diagram where each of the components commutes, opposite direction. Each of these diagrams commutes. So then any two paths you get, for any two objects in this diagram, if you follow any two paths, they lead to exact the same morphism. What this means is, if we're starting from x0, if you go like this, go to y in this way. And then another way to go is follow the same path and go like this way. Actually, this is not a good example that I want to talk about. So let me erase this. Okay. So there's G0 and then eta prime. So the two paths that I want to look at here is one, so starting from this f of x0, we can define a path. This sometimes doesn't work as well as I hoped. So we have a path like this, and then we can define another path that goes from here and go this way, and they will give the same result because they are the same path. So what this means? This means that for every the fn of x0, like this guy, we can define a morphism that goes from x0, f the square x0 to y by composing all the morphism in the path from this object f square of x0 to y. And that will always give the same morphism. And from there, we can deduce what we have here. Sorry about this. I think there's also another synchronization problem. So from there, we can deduce if you define, y is actually a cocorn of the chain that we started with. So this is a chain that we started with. Y is a cocorn where we have from x0, we have a morphism for y, and f of x0, we have a morphism that is defined by eta prime composed with f of a0 and f square of x0, and we have a morphism eta prime, f of eta prime, and f square of a0. F is missing. And so on, we can define like this, and then the argument that I just told you, and these collection of morphisms commute with existing morphism in the chain that we already have. It's like a G0, f of G0. There will be square of G0. And this blue and the yellow line that I showed you on the top, that talk about the commutativity on the third one. I mean, let's just write it here. That's the prime square of I2. No, this is not quite true. Eta prime cube of AC. So we said that this blue and the yellow line that I talk about shows that the triangle here commutes. And you can actually show that all the triangle in this diagram commutes. In other words, we have this Y together with this appropriate collection of morphism is a cocorn. So we said this X fix that we define on the top, we said that's going to be a coordinates. And then in the bottom of the chain, in the bottom, we have a Y, which is the cocorn of the same chain. So that by the definition of a colimit implies there has to be exist unique morphism that goes from X fixed to Y. So that's this unique morphism that we talked about in the theorem. Okay? And we have to prove many other properties that exist stated in the theorem. So we still didn't really prove this number one. And then also we have to show that this H that we just defined, actually I wrote it as a K, and satisfy this commutative diagram. And doing this is an exercise. It's not very easy, but it's an exercise I want you to try. Okay. And then we will deal with this number one a little bit more. Okay. So far we constructed X fix and H. Now what I'm going to do is we're going to construct this row. I mean, that's the important part. That's because that's the part we're going to use the omega continuity of F. Okay, how to build row. So I think, see, yeah, step 3. Row that goes the opposite direction, X fix to unknown. So actually we didn't even build eta. Eta and row. To X fix and row that goes from X fix to F of X fix. And here we are using, I mean, especially construction of row, we are using omega continuity. Actually, the row, the eta, we are using omega continuity. This sometimes. Okay, so we're gonna use omega continuity for eta. So how we do it? So we have a omega chain starting from x0. So we have f of x0, f of g0, so on, and then we have this x fix, and this is relative as H0, H1, H2, and so on. So what we're going to do is we apply functor f to delta. Because f is omega continuous, what we know is that if you apply functor f, what we will get is the, what we're going to get is also coordinates. Okay, so if you apply f to everywhere, x0 becomes f of x0, g0 becomes f of g0, square of 0, 0, cube of x0, and so on. And then the x fixed becomes f of x fixed, and the first guy will becomes the f of h0, second becomes f of h1, third f of h2. So then now we know this is a colimit. Because of omega continuity of the functor f. So why this is important? And if we recognize this is a colimit, then we can start to look at some part of where we started with. So if you look at original delta and only look at the part excluding the first element, and this part looks that it really tells us x fixed, although it's a colimit of the original chain. If we get rid of the first components, if you get rid of this first step from this chain, x fixed is going to be a cocorn of the remaining element, remaining part of the chain. Okay? Because of H0, H2, and so on, they will form all satisfy all the required commutativity conditions. So what does this mean? So we can now, by using this observation, we can write x fixed. Sorry. We can write x fixed, and then just copy this H1, H2, and so on. So we have H1, we have H2, we have H3, and so on. And they are cocorn of this F chain, omega chain F of delta, which is the truncated version of delta. The first step is truncated from delta. And we know this X fixed is a cocorn. Because f of x fixed is a colimit, there has to exist a unique morphism from f of x fixed to x fixed. That's what we will call eta. Okay. Then this eta is satisfied all the required conditions. Okay. So that's how we build eta. And then to build rho, and this we have to notice one more thing, which is if you put x0 to f of delta, okay, so just write it like below. So we have f of delta, which is erase this. So if you put f of x0, f of g0, and then of H2. Now, but one thing we can do is, this is a core limit, but now we can add some extra element there. X0 is the initial object. So from the initial objects, there is a morphism from x0 to f of x0. That was z0. Now, because x0 is an initial object, there is also a unique morphism that goes from x0 to f of x fixed. That's, we call it k. It exists because of initiality of x0. And then because this x, we are adding something because x0 is the initial object, every diagram, this one commutes, this commutes, as well as this commutes. What does this mean? This means that now we can view f of x fixed is a cocorn of the original chain rho, okay, the original chain delta. So we are playing with the two chains, original chain delta and the truncated chain f of delta. By using truncated chain, we show that there exists, we constructed morphism rho, no, eta that goes from f of fixed to x fixed here. And by going back to the original chain delta, we can construct the opposite morphism. This is the f of fixed is a cocorn of the original chain. X fixed was the x fixed is the co-limits of this chain. So there has to exist a unique morphism that goes from x fixed to f of x fixed. That's what we will call rho. And then by using the uniqueness properties of rho and eta, you can prove that it is rho and eta, they satisfy this inverse condition that I just mentioned. It's a bit complex, but the proof idea is similar. The key message that I want to convey to you is proof is a generalization of the proof of this least fixed point theorem in the domain theory. By using this, the generalizing the least fixed proof of least fixed point theorem in the domain theory, we were able to construct this x fixed and h directly here. And then by using omega continuity and playing with the two chains, one is what I called delta, and the other is its truncated version f of delta. And we were able to construct, this rho and the other required morphism eta there. Okay. By looking at f of delta, we constructed rho. So from the perspective of f of delta, f of x fixed is a co-limit, x fixed is cocorn. So that's why we have rho, we have eta. And from the perspective of rho, x fixed is a co-limit. And from perspective of delta, x fixed is a co-limit, f of x fixed is a cocorn. So that's why we have a morphism rho from x fixed to f of x fixed. And then they satisfy the claimed property if you work out the uniqueness and the properties that this eta and rho enjoy. Okay, I hope, it's a bit complex. And then I didn't prove the required property in number 2, but again, if you look at the guaranteed property of the morphism that we just constructed, then from there you can deduce the claimed property is going to be true. Okay, so now the remaining 5 minutes, I will say briefly about how we can instantiate this whole thing to solve the open problem that I mentioned in the beginning. Okay, here's number 4. So we can instantiate what we develop because categorical setup is very general. We can instantiate what we develop in any categories, which includes category of set and category of predomain and category of domain that we talked about. But I mean, that will give us, for instance, I think if we use a category of domain, that will allow us to talk about, I mean, this construction of omega. And in fact, the many things that we did in the previous chapters is using this. But that's not good enough. So we need to talk about some different category, which is a category of embedding projection pairs. That's because if you look at this space of continuous function space from D to D, okay, the problem is that if I mean for this, that's, I mean, this does not lead to a functor on domain. Okay, so these are domain, but I mean, if you just take a function space, it does not lead to a functor on domain. That's because we have a problem about how to map. I mean, we have a problem here for defining morphism action. So what I meant is if we have a more continuous function f that goes from D to D prime. Now from here, we want to induce some functions that goes from D arrow D. So D prime to D prime. But this type of thing is not easy to define. So what should we do? I mean, that was actually one of the reasons why things are not working really well. So the key idea in this DOM EP is that it's an issue. So the key idea is to think about only special kind of morphisms. And what are those kind of morphisms? And they are called embeddings. So these guys are called embeddings. So then embeddings, so this for in this category, objects in the categories are domains, but morphisms f that goes from D to D, D prime, continuous functions. Actually, strict continuous functions, which means the bottom preserving continuous functions from D to D prime, such that it has some property. There exists a morphism that goes opposite direction, D prime to D, with the following property. The first property is if you first apply, I think the best is to give a diagram. First apply F and then G. That gives same thing as identity on D. So this diagram commutes. And then second property is not really a commutative diagram, but it's an order relationship. If you start from D prime, go to D, and coming back by applying F, that gives something smaller than ID on D prime. So in other words, G smaller than equal to ID D prime. So intuitively, this means that if you have a domain D, so this is an ordered domain D, intuitively this condition said D prime is obtained by something adding some extra element on the top. So there are many ways of adding new elements, but all these elements have something which lives somewhere on the top. So that's intuitively what this condition is telling us. And it's also related to so-called Galois connections. If you have, happen to work on program analysis or maybe some symbolic techniques for programming languages. Now, just let me mention one more thing and then finish. So why this kind of category helps? So that in this category, domain of embedding projection pairs, we have objects are domains, but morphisms are some special kind of continuous function strict, which is a bottom preserving, strict continuous functions, which have, this function like G, a companion function G. So F satisfying this property is called embedding. This G satisfying this property is called projection. Now, if we have the reason having this is because if we have this, then we can define a functor. Using function space. Now we can define a functor that goes from dom EP to dom EP, where if we take a domain, it return a new domain that consists of continuous functions from D to D. Then for morphisms, F, we have to define a morphism that goes from, so if F is from D to F. Sorry about overtime, but I want to finish this part and move on to prime. So then we have a morphism that goes from something like this. And then the way we do it, so we have to, given K that goes from D to D, we have to produce something called from D prime to D prime. So we do it is like this. So if we have a K, then we compose with F. So K goes from D to D prime. No, D to D. So I think, let me just write it as a diagram first. So it's going to be a morphism from D prime to D prime. From D prime, we will use something to go back to D. From D, we use K. From D prime, we use F. But now this is the usually problematic part before, but because F is an embedding, there is a projection, corresponding projection. And it also happens that projection is unique. So we use the projection G. So this G and F. So G is the projection for F. So G is the one that exists here. So if we use this composed with the G and F, so that's F, K, and G, and that will define how the functor F should behave with respect to morphisms. So if you do so, it happens that this F is omega continuous, and this dom EP is also chain complete, and it also has a list element. So all the things that I talked about, it works, and you can use it to define some solutions of recursive domain equation that involving this function space. Okay, so that's it for today, and sorry for going over time. And I'll be here a few more minutes, so if you have any questions, you can ask me. So thank you very much.